talking about the ABC conjecture, so let's welcome him.
Thank you. So my intention here is that this be accessible to everybody. The main things you should be familiar with are polynomials, that's not asking too much, and integers and prime numbers. Polynomials maybe in the first half of the talk, but then prime numbers in the second half of the talk. So what I'm going to do is describe some of the history and maybe some minor technical details that surround a very famous open problem, not a problem that's been part of the mathematical thinking for very long. In fact, I think it was 1987 or maybe 88, I was at a conference at Imperial College in London where David Masser, at a problem session one evening, posed this problem and just asked if anybody in the audience knew how it worked or had seen it or knew the answer and so forth. And this is what has become known as the ABC conjecture today. The Riemann hypothesis, of course, is an equally famous problem, much, much older. But the ABC problem really seems to be super impressive because it has many deep, difficult implications. When I say deep and difficult, I mean it implies things that are way beyond what we seem to be able to prove. So to get started, let me begin with a page that's mostly notation. So I'm going to be talking about polynomials. And the important thing about these polynomials, is this focused okay for everybody? I guess so, okay. The important thing about these polynomials is that we should be able to factor them, as I've done here, into many linear factors. And that means we probably should think of the polynomials as having coefficients in the complex numbers. There are plenty of other fields that would work just as well, but for this talk, for simplicity, I'm just going to talk about polynomials with complex numbers as coefficients. So in that case, of course, the fundamental theorem of algebra tells you that if you have a polynomial whose degree is at least 1, then it's going to have a complex root. And if we call that root xi1, then you can factor x minus xi1 out, and you get a polynomial of 1 lower degree. And then you can repeat that activity. And at the end of the day, you end up with a factorization in this manner. So you should keep in mind, and this is actually rather important in this talk, that it's possible for the first couple of zeros to actually be the same complex number. So for example, it might happen that xi1 and xi2 are both zeros. And in that case, we would say it has a zero of multiplicity 2. Well, it's also possible that all the zeros are different complex numbers. But for the purposes in this talk, the case where there's a certain number of xi's that kind of clump together and are the same number is actually interesting. Now, I need to introduce some fairly standard functions that occur in this context. Let's suppose alpha is a complex number. Then the order of vanishing, it's sometimes called, the order that f vanishes at alpha, that's just the number of roots that are equal to alpha. By the way, say for example xi1 and xi2 are the same complex number. You can tell that that's going to happen because when you plug in xi1, you get a 0. By the way, xi1 and xi2 are the same complex number, so it doesn't make sense really to think that plugging in xi2 is different. It's the same complex number. But what you could do is differentiate f and plug xi1 in again, and it's also a root of the derivative. Okay, so derivatives are sort of in the background here. Now, let's go back to this function, the order of vanishing at alpha. Of course, for virtually all complex numbers, this is 0 because the polynomial doesn't vanish there. But for at most n complex numbers, possibly less, but at most n complex numbers, this is some positive integer, which counts the number of roots that are equal to alpha. Here's a little formula that you should all think is kind of trivial. It looks a little strange because I'm summing over complex numbers, which seems crazy. But keep in mind, this is virtually always 0. There are only finitely many complex numbers where this is going to be a positive integer. And then, of course, it'll add up to the degree, because each one of these has to be counted when you add those up. Although some of them may be counted, you may count a 3 at some particular alpha because that alpha occurs 3 times in the list of roots. Okay, now another thing that's interesting here, the set I'm calling Z. Now, that's just the set of complex numbers where the polynomial takes the value 0. And I'm not paying any attention to how many times it takes the value 0 at that point. Okay? So for a kind of a boring polynomial, well, the roots are all different, and so the number of elements in this set is the same as the degree of the polynomial. But sometimes one comes upon interesting polynomials where, it might have degree 1,000,000, but it only has 73 different zeros. So some of those zeros have to occur with large multiplicity or order, as it might be called. Okay, and so I'll try to use this notation a lot. Oh yes, and one before I stop this one. I guess I've already said this, but this inequality down here you should think of as kind of a trivial fact about the set of zeros. So when I put absolute values around the set, that means the number of elements in the set. And that's certainly less than or equal to the degree. Now, could there possibly be a lower bound to this number? Is there any sense in which you could say, well, there got to be a lot of points where it vanishes? Not so far, because, why couldn't I make the polynomial have degree 1,000,000, but it could be x minus 3 to the power 1,000,000? I would just have 1 0 at 3, even though its degree is large. Well, Richard Mason was a graduate student in Cambridge University in England in the early 1980s, and he proved a kind of interesting theorem about polynomials, not about one polynomial, but about 3 polynomials. And one of the conclusions of his theorem was that this set had to be pretty big. Okay, here's Mason's theorem. I'll give a proof of this here in a little bit. And Mason called this the ABC theorem. I'm every once in a while asked, where did the name ABC come from? It has a silly answer. When Richard Mason, a graduate student at Cambridge in 1982, gave a talk about his theorem, he called the 3 polynomials a of x, b of x, and c of x. That's where the name ABC came from. It's nothing deep or delicate. It was just the idiosyncrasy of Richard's choice of letters naming the polynomials. Okay, so here's his theorem. You start with 3 polynomials, a, b, and c. And they have to satisfy some conditions. And this is, of course, a very, very simple condition. A plus b is equal to c. Now, you want these things to be actually polynomials. You got to have some x's there. But technically, 5 is a polynomial of degree 0. Richard didn't want to have that kind of trivial situation occur. So he asks that the 3 polynomials are not all constants. It's okay if one of them is a constant, but at least 2 of them have to have degree at least 1. So it doesn't degenerate just to constants. And then the other condition here, 3, is that they don't have a common 0. Let's suppose, for example, that 5 is a 0 of all 3 polynomials. Well, what you would do then is factor out x minus 5 from all 3 and just remove it and start over again with your new polynomials, which now no longer have a common 0 at 5. And you would just do that activity until you've removed any common zeros. So Richard's theorem just starts with the interesting case. Okay? Not exactly exotic conditions, very easy to understand. Z is the set of complex numbers where one of the polynomials at least takes the value 0. Okay? Because in order for this to be 0, either that one is 0 or this one or this one. So Z is the union of the set of zeros of A and the set of zeros of B and the set of zeros of C. And Richard argued using a little calculus, I'll give the proof a little later, that in fact, if this situation were to arise, the size of the set Z of zeros has to be somewhat big. So in other words, if you have a set of 3 polynomials, and let's suppose they all have degree 50, okay, and they add up in this very, very simple way, and we're not in a trivial situation, so these basically say it's an interesting situation. If you have 3 polynomials of degree 50 that satisfy that equation, then the total number of zeros of all of them has got to be at least, well, at least 51. All right? So why couldn't you have x minus 7 to the 50th power, and then maybe this one has a 0 of multiplicity 20 and another 0 of multiplicity 30. So I've got 3 zeros so far. And maybe we'll have this have 4 different zeros, but each 0 has a high power, the number of times it occurs. So 3 and 4 is just 7 zeros. Well, it turns out that can't happen. Okay? Now, when Richard gave a talk as a graduate student at Cambridge about this, it wasn't at first viewed as a particularly impressive theorem, I think. But he made some observations, not the one I'm going to do here, which started people thinking about this as maybe a little bit deeper fact than it appears. This is just a little example that I wanted to toss up to show you that the inequality that Richard got was sharp. So here's an actual choice of A, B, and C. And if you try squaring this out and adding A to it, and you'll get another square, and you fold it up again, and you'll get C. So A plus B really is C. Let's see, this has degree 2n. Here n is your favorite large positive integer. And if you square that out, it'll have degree 4n, and this has degree 4n. So the maximum degree is 4n. Now let's count the total number of zeros. Well, that has as its zeros the 2n roots of minus 1. So there are 2n distinct zeros. And that has as its roots the 2nth distinct zeros of plus 1. So far I've got 2n zeros here, 2n zeros there, 4n zeros, and that has only one 0 right at 0. Right? And so the total number of zeros is 2n and 2n and 1, which is 4n plus 1, and that fits the inequality perfectly. There's equality in the inequality. So Richard's theorem is sharp in that sense. Okay, now, where is this going? Well, here's a rather intriguing application. This is Fermat's last theorem for polynomials, not Fermat's last theorem for integers as Fermat originally imagined it, but it's perfectly reasonable to say, what if I have 3 polynomials? And to make it sound and look like Fermat's original problem, let's shift and let t be the variable of the polynomial. There's still complex coefficients. So could it happen that there are 3 polynomials, x of t, y of t, z of t, such that the famous Fermat equation holds? Well, if n is greater than or equal to 3, no. Fermat's last theorem is actually a theorem. if n is greater than or equal to 3, as Fermat conjectured, of course, for integers. Here again, I'm avoiding trivial situations. So I don't want to say, well, I can find a complex number, which is a polynomial of degree 0, and another complex number, a polynomial of degree 0, and a third one to make that work. Yes, of course you can. We're worried about polynomials here, not degenerate cases of polynomials. So we require the polynomials to have some positive degrees there. And of course, again, if x, y, and z were polynomials and they all vanished at 11, well, I could factor x minus 11 or t minus 11 out from all of them. I'd end up with a t minus 11 to the nth power, but I could remove that and put myself in a situation where they don't have any common zeros. Well, let's see what Mason's inequality says. I take the maximum degree of x to the n, which of course would be the degree of x times n, and then I compare that with the degree of y to the n and the degree of z to the n, and I take the biggest one, and Mason's theorem says the total number z of distinct zeros minus 1 has to be greater than or equal to that number. Okay, now how are we going to estimate the size of the set of zeros? Well, very easily. And here's the magic step right there that makes it work. Of course, z is the set of complex numbers alpha where the product vanishes. But the n is irrelevant. Toss the n away. It's the same set. All right? Okay, but now, what can we say about the set of points where one of the x, y, or z vanish? Well, the number of elements in that set is at most the degree of x plus the degree of y plus the degree of z, isn't it? Right? That would happen, in fact, if they had their own private set of zeros, no overlaps. Well, that sum is certainly less than or equal to 3 times the maximum term, since I've got 3 terms. And so if I combine 1 and 2, I end up with this inequality down at the bottom. And you can see by looking at it that that inequality cannot hold if n is 3 or more. All right? If there's a solution, n has to be less than or equal to 2. Okay? And that, if you think about it, is Fermat's last theorem for polynomials on one page. Right? By the way, when Mason proved his theorem, Fermat's last theorem for polynomials was known, but it wasn't known on one page, and it wasn't known with just sort of elementary mathematics getting involved. And so, well, that attracted considerable attention. Now, let me also indicate another application. You know, you might say, well, Fermat's last theorem is a very special problem. But here's a more general problem. I'll call this the generalized Fermat equation. And there aren't going to be any solutions to that one either, in polynomials at least. And by a generalized Fermat equation, I mean the exponent on the polynomials x, y, and z can be your favorite positive integers. The only request I'm going to make is I got to avoid things like 1, 1, 1, obviously. I have to avoid a few more than that. But in any event, I'm going to ask that L, M, and N have the property that the sum of their reciprocals is less than or equal to 1. Notice 3, 3, 3 qualify. But of course, so does 3, 5, 2. Right? So I have a little more flexibility. But Mason's inequality shows that there are no polynomial solutions to that kind of Diophantine equation, as it's often called. Here's the argument. I don't have an n out in front anymore, but still, the maximum of that degree, and this degree is on the left here. And then this is the number of elements in the set of zeros, just as before. And I can play that same magic trick. The set of zeros doesn't feel L, M, and N. You can eliminate those, and this describes exactly the same set. Okay, so I can count the number of things in Z, or at least I can bound it from above by the sum of these degrees. Now I have to work a little harder this time. Not much, but a little. So if I use these inequalities in just the right way, I have as an upper bound for the number of zeros the sum of the degrees. And then I'm going to introduce the L's, the M's, and the N's. And then I'm going to take the maximum of the numerators. All right? And whatever that is, that means that two of the numerators are going to go up to the maximum, and then the one that is the maximum will stay the same. And then I'm going to add up 1 over L plus 1 over M plus 1 over N. But by the starting hypothesis, in order to make sure that the L, M, and N are somewhat big, I'm going to make sure that the sum of their reciprocals is not too big. And in fact, I ask that this number be less than or equal to 1. And so here's my upper bound. And when you put that in Mason's theorem, you get max less than or equal to max minus 1, which of course is always false. So as long as the exponents L, M, and N have the property that the sum of their reciprocals is less than or equal to 1, they don't all have to be the same. Again, Mason's inequality shows there are no polynomial solutions to the so-called generalized Fermat equation. Let me now just sketch out the proof of Mason's inequality. Mason later proved a theorem with many polynomials in it. That's a little harder to prove. With just 3 polynomials, you have to introduce, or you ought to introduce, the Wronskian of 2 of them. You might have seen the Wronskian in courses on differential equation. It's used to measure linear independence of functions. We could give the proof without introducing the Wronskian concept here and just say, well, I'm going to talk about a polynomial W, which is A times the derivative of B minus B times the derivative of A. But it turns out in the larger version with more polynomials, in order to sort things out, you have to use a larger determinant, which is a kind of well, it's still a Wronskian, basically. Anyway, so the Wronskian is a certain polynomial, and using elementary identities about determinants, well, really this comes from the fact that A plus B is equal to C. All 3 of these represent the same polynomial that I'm calling W of x. Right? So for example, C is really A plus B, so you can replace C with A plus B, and here you can replace its derivative with A prime plus B prime, and you'll discover it just repeats that again. Okay, now, here are some elementary inequalities. If you have a complex number alpha, I think this inequality should be almost self-explanatory. Remember, A, B, and C cannot have a common 0. So for one of the polynomials, A, B, or C, the order of vanishing at alpha is 0. Well, let's say it's C, for example. So you can just ignore that because that's a 0. Okay, now the Wronskian is A, B prime, and that B prime, when you differentiate it, that lowers the order of vanishing by 1. And then the other term was B prime A, and the same thing happens. And so the order of vanishing of A, the order of vanishing at B, minus 1 is a lower bound for the order of vanishing of the Wronskian. Okay, step 2. Let's just sum both sides over the set script Z of zeros. Well, then we arrive at this point, and you'll notice that this minus 1 gets summed, well, the number of zeros times. That's why it makes an appearance here. Okay? Now, you know, on one of the earlier slides, I observed that if you sum the order of vanishing over all the roots of A, which must be contained in Z, you get the degree of A. And the same words apply to the sum here. You get the degree of B, and here you get the degree of C. Nothing happens there. This one is a little more subtle because, of course, Z does not necessarily contain all the zeros of the Wronskian. Z is the roots of ABC. The Wronskian's a little different creature. But I have an inequality here, and I know that the degree must be greater than or equal to the total number of zeros accumulating in Z. So the inequality says this could go up, and that's consistent, of course, with the direction that it's pointing in. Okay, lastly, we can compute, or really estimate, the degree of the Wronskian. It's the degree of this combination, and of course you can see that the degree of a product is, of course, the sum of the degrees, but the degree of the derivative has gone down by 1, and that applies to both these terms. You might, if you're not sure about these things, you might just work it out on a piece of scratch paper. It's pretty simple. But anyway, an upper bound for the degree of the Wronskian will be the degree of A plus the degree of B minus 1. Well, okay, put this over here, and you can cancel degree of A and degree of B, and you get that at the end of the day, right? Now, it's entirely symmetrical with respect to A, B, and C. So if I can derive this with degree of C there, I can surely go back and start over again and derive it with degree of A and with degree of B. All right? So I'll just pick whichever one is most favorable, or to maybe say it a little differently. I can write the inequality this way, but since it's completely symmetrical in ABC, I must also have these inequalities. I'll just pick whichever one is biggest, the maximum of the degrees, and that must be less than or equal to the number of zeros minus 1. And that's the proof of Mason's theorem. So we use properties of derivatives. Well, I didn't really need to use the determinant. I could have just written out what it was with two polynomials. We differentiated. We used a little bit of calculus at a very elementary level, and that's about it. So, as I said, I think when Mason first showed people this theorem, they weren't too impressed because it seemed to use such elementary mathematics. But the proof of Fermat's last theorem for polynomials on just one page, that interested people. I want to move on to the conjecture here in just a second, but for those interested in such things, you might ask, could Mason's theorem be formulated and proved for many polynomials, not just 3? And the answer is yes, and here it is. So in this version, capital N is 2 in Mason's theorem, but in this version, capital N is some large integer. You have many polynomials. Pretty much the same rules apply. I wrote A plus B equal C, but you know, the C could be moved on the other side, right? And just name minus C your new C. Because the plus or minus signs in front don't really matter, of course, in the argument. So you could also have an hypothesis like this. Now, the condition about non-triviality is a little more complicated when you have many polynomials. One way to say it is these polynomials are linearly dependent, but the only linear dependency is this guy. Or in linear algebra language, they span a vector space of dimension n, right? One fewer than the number of polynomials. Okay, and third, they don't have a common zero. Again, script z is the set of all possible zeros of any of the polynomials, a finite set. And then the generalized Mason inequality asserts the maximum of all the degrees is less than or equal to, well, now this is a little more complicated. This is a binomial coefficient here, n over 2. So that's n times n minus 1 over 2, a quadratic polynomial n. In Mason's situation, n was 2, right? 0, 1, 2 are the three polynomials. And so this binomial coefficient is 1 and disappears. But when you have more polynomials, the natural proof produces this number here. As far as I know, as far as the computers can tell us, this should probably really be a linear function of n, not a quadratic function of n. But the state of the art today is that this is essentially the best we can do, a certain quadratic polynomial n there. Any questions about what's going on here with, yeah?
So are you saying that the binomial coefficient n of n2 is not the best estimate? That you could possibly find something?
The computer doesn't find examples showing you really need a quadratic polynomial there. Yeah. If you believe the computer does a good job of searching, it seems from the best evidence that that probably can be replaced by a linear function. You know, there are even some proposed examples. I think something, I may not remember this right, but something like 5n plus 8 or something like that, I think actually seems to work for polynomials of degree less than 100. Yeah, so. Okay. Let us move on now to the ABC conjecture. Well, actually, I'll just take 1 second for those who would like to learn more about this. Here are some papers. I think this one in the middle by Granville and Tucker, if you just go to the AMS website, you can easily pull that one up. That's probably the nicest one that really kind of introduces the subject for non-experts and has quite a few interesting examples beyond Fermat's theorem of important problems, mostly in number theory and arithmetic geometry, which can either be solved or great advances can be made if the ABC conjecture that I'm about to talk about turns out to be true. Some of these, this one is probably a little too technical. That's also a pretty good survey article. And this one should be mentioned. Stothers proved a theorem that I will call similar, not the same as, similar to Mason's theorem in a somewhat different subject where polynomials are also relevant. But he did not really quite see the connection to Fermat's last theorem and other things that Mason saw. And that Stothers really contributed something nearly the same wasn't discovered for a while. I think it was about 15, 20 years after this paper that number theorists realized that if you just looked at his stuff the right way, you would see special cases of Mason's theorem. Anyway, okay, so let us move on to the conjecture. Now, one of the things that guides people in mathematics is analogies. And one of the famous places where you can find a lot of analogies is between the ring of polynomials and the ring of integers. This can be expanded in many, many ways, but just to keep it at a simple level, many theorems about the ring of polynomials, say with complex numbers as coefficients, have analogs for the ring of integers. For example, in Mason's inequality, it's based on your ability to take a polynomial and factor it. And I've changed the notation a little bit. Instead of thinking about xi1, xi2, and so forth, as I did before, as the zeros, possibly some of them are the same number, I'm going to group things together this time. And so think of alpha 1, alpha 2, I guess that's alpha little n, as the distinct zeros. And so the exponents up here are recording the order of vanishing at those points. They're recording the number of times that alpha 1 is a 0. it's a 0 E1 times, and so forth. Okay, and then of course it also makes heavy use of the fact that there's a relationship between the degree and the amount of vanishing. So E1 plus E2 and so forth is going to be the degree of that polynomial. Now, when you're working with integers, I think the natural analog would be the prime factorization of the integer. In fact, you can make that quite explicit. The x minus alphas are the irreducible complex polynomials. And irreducible is an analog of prime in a slightly different setting. So we might try to set up the same situation and see if the same proof would work. So here's an integer a factored into its prime factorization according to the fundamental theorem of arithmetic. And we might say, trying to adopt the same notation, the order of vanishing of a, it isn't really vanishing, of course, but anyway, the order of p as a factor of a, maybe sounds better, is the number e, which is, well, the exponent on p when I write it out as a product of primes to powers. Okay? Now, I don't quite have this. It's a little bit different. Instead, it looks like that, because the primes come in different sizes. Right? The zeros of a polynomial are sort of all the same size. But some primes are bigger than others, and so they need to be put in here with a different weight, so to speak. But then that's still a version of prime factorization, right? The absolute value around the a just simply means I'm going to ignore the plus or minus sign that's there. Okay, and so that is going to be my analog of this basic formula. So here's a first try at an analog for integers of Mason's theorem. This turns out not to work, but anyway, this is the first attempt. A, B, and C are integers. They satisfy this deep equation. A plus B is equal to C. Okay, now we have some conditions that avoid triviality. I don't want them to be all 0, a reasonable assumption. So A, B, C are interesting numbers. And I don't want them to have a common prime factor, because if 7 were a divisor of A and B and C, I would just remove the 7, factor it out, and start over again with a new choice of A, B, and C that no longer had 7 as a common factor. So we're assuming that's going to already be done. Okay, and then what do we do about the 0 set? Well, we look back at the factorization and we recognize that the zeros of a polynomial correspond to those irreducible factors. So the analog for an integer should be the primes which divide A, B, or C. That seems pretty reasonable, I'd say. So now what we want to do is give a lower bound for the number of primes. And I guess if we were to just take Mason's inequality as kind of a guide, we might try something like this. The maximum of remember the logarithm appeared in our sum formula, so the maximum of the logarithms of A, B, and C, that's kind of the analog of the degree, is supposed to be less than or equal to, well, I'm not going to count the number of primes for the simple reason that, as we've seen, not all primes are the same. Some are big, some are small. That doesn't occur with polynomials. Sort of the zeros are kind of the same, but for integers factored into primes, the primes have a magnitude that kind of comes into play. So instead of counting just the number of zeros, I'm going to count them with a weight that seems appropriate. And the weight will be the logarithm of the prime. Not a very big weight. Increases very, very slowly, but still I think it should be there. And then I could get rid of all the logarithms by applying the exponential function, and I arrive at this version. This is a little simpler to look at because the logs have been removed. The logs were kind of there for inspiration, but now I no longer need them. Well, the trouble with this inequality is that it's just not true. All right, here are some examples, and these examples all show that that inequality that I had up on the previous slide is just not correct. It is possible sometimes for, well, for example, 2 to the 5th, that's 32, plus 49 turns out to be 81, 3 to the 4th, right? You can try it, you're going to see that it works. And if you put that back into the proposed Mason theorem, it shows that the proposed Mason theorem is not right. A mild way to get out of this would be to imagine that the truth really requires some constant k here, right? Maybe 1,000. If you put k equal to 1,000, none of these examples will defeat that. But there are other examples that will, unfortunately. Let's just experiment a little bit. And here's our proposed conjecture. Remember, A, B, and C have some hypotheses connected with them, the most important one of which is A plus B equals C. But 6 is still not correct. It doesn't matter what k you choose. If you choose k to be 1,000,000, I can still defeat it. To do it, choose A to be 1. No prime factors there. B to be a big power of 2, just 1 prime factor making an appearance. And, well, sorry, I shouldn't say it that way because it's 2 to this power minus 1, so that actually could have some primes, and it's really the 2 that just has 1 prime associated to it. Well, but of course you can see that A plus B is equal to C. Now, in elementary number theory, you might remember Euler's theorem, which in this setting tells you that the integer q that occurs here, squared, has to divide b. And so that means that when I'm counting primes dividing b, I can choose q to be a prime here, the prime q occurs in b twice, but of course I'm only going to have to count it once, right? Because on the right-hand side here, the p's just appear once if they occur at all. If they occur to a high power, the power is ignored. So by Euler's theorem, the product of the primes here is going to be bounded from above by that expression. And if you take the maximum of A, B, and C, you'll get this expression. So the constant k would have to have the property that this inequality is correct for every prime q, but of course there are infinitely many primes q, and if I choose q big enough, I can cause the right-hand side to be less than the left-hand side, regardless of what k you choose. All right? Once you tell me that k is 1,000,000, I'll go out far enough and find a prime q so that the right-hand side is is smaller than the left-hand side. Okay, so that's still not going to quite work. Well, various efforts along these lines were made by various people, mostly by Masser and Oesterle, who more or less, I think, at the same time proposed a slight variation of Mason's inequality. And this one has definitely withstood the test of time. And this is what we think of as the ABC conjecture for integers today. It's more or less what I've been speaking about, but modified with a friendly epsilon there. So for every epsilon greater than 0, there's a positive number k, but now k gets to depend on epsilon, such that if a, b, c are integers, a plus b is equal to c. They're not all 0, and they don't have a common prime factor. Right? These just avoid trivial situations. Then the maximum of the absolute values of a, b, and c should be bounded from above by, well, it's pretty close to the product of the primes. but I'm going to give myself a little help by raising it to the power 1 plus epsilon. And if epsilon is really small, I might also need a little help from this constant k being big. This is not known for any value of epsilon and k. It's not known for epsilon equal 1,000,000, for example, which, yeah. Let me just indicate some consequences. Let's just experiment with a simple case. Suppose we knew this for epsilon equal 1 and k equal 1. Okay, and just see where it leads. So this is the ABC conjecture as it has been kind of formulated and reformulated and reconsidered over the years, and this has been stable now for about, I think, at least 25 years. So I think this is the problem right here. They're proposed relationships between epsilon and this constant, but they're kind of technical and mostly speculation. But anyway, let's just continue assuming that something like this is true when epsilon is 1 and k is 1 and see what we can get. For example, we can get Fermat's last theorem. So let's assume that a, b, c are non-zero integers with no common prime factor. A to the n plus b to the n is c to the n. So if the ABC conjecture with epsilon equal 1 and k equal 1 is correct, then the maximum here would be less than or equal to the product of the primes that divide the product ABC. And epsilon is 1, so now the exponent here becomes 2. Well, I guess you would have to say that the product of all the primes that divide ABC is certainly less than or equal to ABC itself. Right? That's trivial. And, well, instead of using ABC, I could just pick out whichever factor was the biggest. And then I want it to occur 3 times in there. And together with the 2, that means the maximum to the power 6. Well, that's pretty good. That's Fermat's last theorem for exponents greater than or equal to 7. Of course, Fermat's last theorem for exponents less than 7 was known in the 19th century. Right, so you got a little more work to do. You have to prove Fermat for exponents up to 7 by some other means, and then you get the ABC conjecture to do all the other cases for you. All right? And you can experiment with this if you choose, epsilon equal to 5 and k equal to 7. Well, this guy is going to get a little bit bigger. But I think when Wiles proved Fermat's last theorem, I think it was already known for exponents pretty big, I think in the range of 200,000 or so, roughly speaking. So, yeah. But anyway, this certainly is an example which indicates the potential power of the ABC conjecture. Fermat's last theorem on 1 page of paper, basically. Here are some other things. This is maybe some cases a little bit technical, but this is a list of 4 results in number theory, modern results, I guess in one case an unsolved problem down here at the bottom. So Falting's theorem, which is a proof of the Mordell conjecture, could be given in effective form. Right now, a curve of genus greater than or equal to 2 over an algebraic number field has finitely many points, but there's no way to bound the number of points. It's kind of a compactness argument that says it's bounded. ABC would allow you to compute a bound. Dewey-Siegel-Roth, that's a statement about how well algebraic numbers can be approximated by rational numbers. And again, it's not effective. It's due to a very indirect argument that can't be given in a quantitative form. But if you knew ABC, you could go back to that ancient problem and give an effective version of it. That's a very, very, very hard issue to deal with, the effective form of Dewey-Siegel-Roth. And Baker's theorem on linear forms and logarithms could also be sharpened. That's even a little more technical. And then another problem that occurs in analytic number theory a Dirichlet L function. That's a Dirichlet series related to the Riemann zeta function. But there's a mystery about these things. There's a certain zero that might occur in what's called the critical strip between 0 and 1 on the real axes. And it's called a Siegel zero. No Siegel zero has ever been found, but we have no proof that they don't exist. But if the ABC conjecture is correct, then Siegel zeros don't exist. That's what everybody sort of believes. Anyway, I mentioned these 4 problems. They're problems of current research interest, and ABC would have an implication for all 4 of them. Finally, my last slide here. How close can we come to ABC? Is there some theorem that is in the right direction? There is, actually. It was proved by Cam Stewart and you in 1991. It has exactly the same hypotheses that I've been talking about, well, except that in this case, they prove there exists a constant k greater than 0 and a constant L greater than 0. And if A plus B is C and we have these non-trivial conditions or conditions that put us in an interesting situation, well, not quite what Mason's theorem does, but the maximum of ABC is less than or equal to, well, instead of the product of the primes to the 1 minus 1 plus epsilon, we have to put in the exponential function, which of course makes things get really big. So if you've ever worked with inequalities and you're trying to show that some function is less than x and you're forced to accept the weaker result, then it's less than e to the x, you know, you're way off, right? Well, but on the other hand, this is actually a correct inequality with a proof. Right? The ABC conjecture is without a proof. It's just a conjecture. And this shows that we're really today, or at least it's one way of showing, that we're rather a long ways away. All we got to do is remove that exponential function. But of course, that is a big, big problem that isn't probably going to be taken care of by some simple kind of argument. Okay, thank you very much. Yeah.
Did the generalized Fermat's theorem for polynomials, was that known before Mason?
I don't think so. I don't think. Well, I'm not sure anybody tried to prove it. Yeah, Fermat is so famous that, of course, Fermat for polynomials was an interesting problem in the development of algebraic geometry and so forth.
Is there such a theorem for Fermat's theorem for integers?
Yeah. If the ABC conjecture is correct, you can formulate a generalized Fermat theorem. The situation 1 over L plus 1 over M plus 1 over N less than or equal to 1 will have to be altered a little bit and turned into something like 1 over L plus 1 over M plus 1 over N is less than or equal to, you know, like the epsilon or something like that. So it has to be rather a lot smaller. But yes is sort of the answer. But as you can see, some modification will be necessary in the integer case because the proposed ABC conjecture is not quite as clean and simple. Yeah. So, yeah.
Do you know how close the word proof is to being verified?
Well, I did talk with some people who are very good mathematicians and who have tried to understand his proof, and they just said they gave up after a few pages because it seemed incomprehensible. So I think the jury is still out. Yeah. You know, I don't know myself. I guess my own feeling is that there are so many deep results that would be greatly improved by ABC that if you can prove ABC in 100 pages, I'd be impressed with that. That seems unlikely. Well, okay. Yeah. Maybe. I mean, these things sometimes happen. I guess the faultings proof of the Mordell conjecture is probably an example of something that was kind of a bolt out of the blue that surprised everybody. Usually, big results are the result of many people working over a period of years, and it gradually begins to formulate, and somebody does the last big step and gets the credit. But I would say that's a more likely scenario if ABC is going to be proved in our lifetime. Yeah, it seems like if it's true, it's certainly one of the deepest facts we will know about the integers.
What's the first one?